All right, welcome back to the PyChain introduction track. Hopefully you have gotten so much value out of this day so far, and I would like to welcome the next speaker, Troy, to the stage. Troy.
Hey everyone, today we will be talking about how you can write better smart contracts by checking them with Slither's Python API. I'm Troy Sargent. I'm a security engineer at Trail of Bits, and I work on the blockchain team, and also we review smart contracts. I contribute to our tool, which we'll be going over today, Slither. You can connect with me afterwards on Twitter or email. If you're not familiar with Trail of Bits, we're a security firm and we help organizations build high assurance software. So one of the ways that we do that is we use program analysis techniques like fuzzing, static analysis, and we apply that to a wide variety of execution environments and languages, ranging from the EVM to zero knowledge, stuff like SIRCOM. So today we're going to be going over first, what is Slither, how it works, how you can use it, and then we'll wrap up. So first, what is Slither? So Slither is a static analysis framework for smart contracts. And by static analysis, all I mean is that we don't actually execute the smart contract. We just look at the source code and we make determinations about properties or characteristics, and we can ask questions about it and get answers just from the source code. So some of those things that we might ask are there any vulnerabilities in this code? And Slither can detect certain bug patterns that may be exploitable and result in hacks. It can also detect gas optimization. So we want to save as much gas as possible because it costs users money, and we can detect ways to make code more efficient with Slither. Another thing that Slither is useful for is during code review. So at Trailbits, we use this tool for all of our smart contract reviews, and we can get a high-level overview really quickly, and we can also write custom queries about the code and tailor it to our client's code. So Slither is not proprietary, it's open source, and you can download it through GitHub or pip very easily. So a little bit more about the vulnerabilities and optimizations. We have about a little over 80 detectors, and we support basically every version of Solidity that you would probably be coming across, so that the compatibility shouldn't be an issue. And whatever framework you're using, whether that be Hardhat, Brownie, or Foundry, we can compile your source code and give it to Slither without any weird integration issues. And it also supports platforms like Etherscan, so contracts that are already deployed and they have verified source code. We can run Slither against them and see do they have any vulnerabilities, and we can look through those. And it also supports other blockchains that have Etherscan-like platforms like Arbitrum or Optimism. So whatever blockchain you're on, Slither likely supports running on there. So now we're going to get into how it works. So this is a diagram of kind of the pipeline of what is happening when you run Slither. So going from left to right, what we're seeing is that we take smart contract source code and we give it to the Solidity compiler, and we ask for some information back, which is the JSON format of the abstract syntax tree, which is not all that important, other than it's just a compiler format that we can use to recover information from, like what contracts are in this code base, what functions do each contract declare, and what do they call. And then we can even get more granular information, like what variables are read and written in which functions, and really advanced stuff like tracking the data flow through a program, like how does this variable impact another? Does a user input somehow influence the execution result of this program? And so all the information is kind of bundled up, and we transform it to what's called the intermediate representation, which again is a compiler format that's just more conducive to analysis than Solidity source code. And so we can ask those questions about our code that we're interested in. And that's where all the nice things that we have out of the box, like the vulnerabilities and optimizations and third-party integrations occur, is against this intermediate representation. That's what we'll be analyzing and asking questions about, and ultimately finding out, does our code have bugs in it or things that can be improved? So today we're going to be using an example of actually something that happened recently. There was a hack for about $250,000 on Ethereum, and the smart contract is it's called an alarm clock. And sort of the idea of this contract is that users may want to schedule actions to be performed at certain intervals. Say like every day you want some action to be performed. So users could upfront deposit and request that this action be performed at some later time in the future. But inevitably, there may be some reason that the action is never performed. So the developers wanted to provide a way for users to cancel and get their money back. But not only did they want users to be able to do that, they wanted anyone who wanted to do it to get a reward for essentially returning the funds back to the user. So when they did this, they decided to subsidize the gas cost of performing this action and to compensate people for essentially canceling some stale action that someone had scheduled, but it's never going to happen. So it'll get canceled. So some interesting things about this contract are this refund mechanism. And one of the things that is subtle here, but that the developers evidently missed, is that there actually is a user input to this cancel and refund transaction. So this object, the transaction gas price, actually is something that the user can designate when they send a transaction, and they can cause the amount that they receive as compensation to increase. And so we're going to try to discover this hack with Slither. So before we do that, we want to get kind of a high-level overview of how you can use Slither. So sort of the hierarchy here is contract, function, node, operation. So once we've imported Slither, we can run it on a contract, and then we have access to all the contracts and all the functions of each contract. And then we have, for each function, a control flow graph, which has nodes in the graph. And all of those nodes have operations, like what is being executed, what's happening within those nodes. So this is that function that we're interested in sort of visualized as a control flow graph. And since there's not any ifs or loops or anything like that, we just have a straight path through the code that we're going to execute one after another. So at the highest level of the hierarchy that I just mentioned, we have the function, and within that we have the node, and then the most atomic unit that we're interested in is the operation. So I mentioned earlier in this pipeline of information recovery, one of the things we track is the data dependency of variables. So we have this transaction gas price, which I already kind of hinted at, that it's a user input that they control, and we can kind of track how this influences the program. And we can say that because we're multiplying by a user controlled input, that actually causes this value in the function cancel and refund, the value reward owed that we're calculating here, it causes it to be controlled by the user. And then we have this operation, which is transfer, and we send funds to the caller. And that's obviously a sensitive operation because we're transferring money to an arbitrary user. So we want to be confident that this value is being calculated correctly. But as we've just stated, it's actually being influenced by user input. So by tracking how the data depends on user input, we can ask ourselves, anywhere in our program, does a sensitive operation use user-controlled input? And that's actually the root cause of this hack, is that we calculate how much to reward someone with a value that they control. So they can just increase it and we'll send them more money. And so we're going to try to only catch this bug once. And we're going to ask ourselves, how could we prevent this from appearing in other code bases or from being reintroduced into this code base after we've found this bug using Slither. So we can see how this snippet of code is translated from left to right into Slither's intermediate representation. And we're going to try to find this transfer operation and see, does the value, the amount that's being sent to the user, does it depend on user input? So the question we're asking really is, can the user manipulate refunds? So sort of in pseudocode or English, what we're looking for is we're going to check that all transfer operations are not tainted by user input. So again, we're going to invoke Slither on our smart contract, the alarm clock, and we're going to ask Slither to give us this contract by its name. So once we have the alarm contract, now we can go through that hierarchy and we can look at all of the functions and all of the nodes in each of those functions. And then we can look at the operations. And the operation that we're interested in for this question is transfer, because it's sending funds to the user. So we're going to look for operations that are transfers. And then we're going to use this built-in analysis of Slither about data dependency. And we're going to ask, does the amount or the operations call value, does it depend on the user input, which is transaction gas price? And when we run this on our smart contract, what we'll see is when we run this script, it'll print out and say, it'll raise a warning, an alarm, and say, this operation is using a tainted input in this function. And you can see that down at the bottom. And you can also see this if you run the script against the contract, the live contract deployed on Etherscan, that it will raise an alarm that you should fix it. And we can also reuse this script across any code base and see if this vulnerability exists anywhere. So this is an example of how you could, one, catch the vulnerability, and then two, prevent it from being reintroduced or happening in another code base. So in summary, what was Slither? It was a static analyzer. We're not executing your code. We're just looking at the source, and it's specifically for smart contracts. And there's a lot of built-in analyses. The one we looked at today was data dependency, and we can track how user inputs affect the execution of programs, and we can see if anything sensitive is being influenced by users, because that may indicate that we have a vulnerability. Again, it supports most Solidity versions and frameworks, so it's very compatible and it's actively maintained. So if you have any issues, you can open one and we'll respond, or if you just have questions, we'll answer them. And then this has been a very short demonstration just for the time constraints, but we have a lot more resources on a repository called Building Secure Contracts, where you can go through some exercises with Slither and get familiar with its API, and you can use it. If you have any questions or ideas or you need help, you can reach out to me. We also have a Slack channel called Empire Slacking, and you can connect with any of the TrailBits employees there. And then finally, all of these slides are available along with the scripts and the source code to reproduce this for yourself. They're available on the TrailBits publications section, and you can find the slides there. Thank you. That's all.
Awesome. Thanks so much, Troy. We have one question. What Solidity parser library do you use for source code, AST? And then they said on slides, there's a box labeled as Solidity compiler, though the output is labeled as AST, not bytecode. Is that one the parser, perhaps?
Yeah, so we give the source code to the Solidity compiler, and it parses it, and it generates a compiler format known as the AST, which stands for abstract syntax tree. So that's used for that inevitably by the compiler will be transformed to bytecode, but we don't actually do analysis on bytecode, we actually take the abstract syntax tree and we parse it. So it's a JSON format. So we parse this JSON object into another format called Slither's intermediate representation, which is, again, just another format that you can, it's more concise and well structured than source code. Like there's a lot, it still retains all the meaning and like what we're interested in. So we're not like, if you're looking at bytecode, you lose a lot of the meaning of the source code and you have to recover information, and it's more difficult. So there's trade-offs there, but we are analyzing against our own intermediate representation that is generated from the abstract syntax tree.
Awesome. And then another question came in. How do you see support for other languages besides Solidity?
Yeah, that's one thing that we're definitely interested in long term, is supporting other smart contract languages. The intermediate representation is designed for any smart contract language, probably within the EVM. So support for something like Viper would be nice, because you get out of the box a lot of things like vulnerabilities and optimizations, and that's sort of how compiler development has moved historically. Is if you look at something like LLVM, there's a sort of shared intermediate representation, and people can target that for their source code and lower it, and then you can get the benefit of a whole bunch of people working together on stuff like optimizing code. So yes, long term, that would be a great goal to have, is to support languages besides Solidity.
Awesome. Well, it's definitely a hot Viper winter. Someone else asked, it seems like there's a lot of this logic could theoretically be applied to Viper. Well, oh, I guess it's the same question. Could Slither be adapted to support another language? So it's pretty much the same question from before. I don't know if you wanted to speak on like other languages like Rust or Move.
Yeah, I mean, we have like sort of there's work in progress on Viper, but it's never really like, if people are interested in it, then you should I guess keep bugging us about it maybe, and we'll work on it more, but it just has never been historically prioritized. But yes, like other languages that are targeting the EVM, instead of going to the Solidity compiler's representation, which is Yule, you could target Slither IR, and then you could generate code from there, and then everyone would share a code gen pipeline, and benefit from also having the analyses that are more sophisticated than available in the Solidity compiler.
Awesome. Well, thank you so much, Troy. If you would like to ask Troy more questions, meet us in the face-to-face room, and yeah, enjoy the rest of your conferencing.